Everyone, let's discuss the topic nonlinear optical effect. When light propagates through an optical dense medium, the electric field associated with the wave E induces dipole in the medium. The polarization P thus induced is directly proportional to E, that is P equal to alpha E, where alpha is called the polarizability. Hence it is the linear polarizations. At extremely high electrical intensities, the polarization P becomes nonlinear and is expressed as P equal to chi1 E plus chi2 E square plus chi3 E cube. Chi2, chi3 are the nonlinear polarizability. These tensors represent how the medium distorts in response to the electrical field. Then, high electrical field, example 4 into 10 raised to 10 watt per centimeter square, are required to observe nonlinear effects like nonlinear Raman scattering. Such a high field are achieved using Gen pulse laser. Nonlinear interaction can lead to new optical effects including higher harmonics. Then the contribution to P from hyperpolarizability and second hyperpolarizability terms depends on the power of electric field strength higher than the first. Therefore, these contributions are said to result from a non-linear interaction of the system with the electrical field. Then let's discuss the frequency generation by a nonlinear optical techniques. Then harmonic generation. Second harmonic generation. The electric field caused by a riser with a frequency nu can be represented as E equal to E0 sin 2 pi nu t, that is E0 sin omega t, where E0 is the maximum amplitude. And the second order term is chi2 E square is equal to chi2 E0 square sin square omega t. That is chi2 E0 square by 2 1 minus cos 2 omega t. That is the induced polarization in the second order is the sum of the constant term and a term oscillating at a frequency 2 omega. This reveals the existence of the electromagnetic field radiating at a second harmonic frequency 2 omega of incident laser beam. This phenomena is called frequency doubling or second harmonic generations. Then the crystalline materials ADB, KDB, potassium penetrate, barium borate and lithium novates are used for frequency doubling. Then let's discuss the next topic, hyper-Raman effects. When a molecule is illuminated with a radiation of frequency nu0 from a focused giant pulsar, it gives rise to a scattered radiation at frequencies. Then, hyper-Raman scattering is a nonlinear optical process that involving the second order nonlinear susceptibility chi2. The electric field E interact with the molecular vibration leading to the scattering at a different frequency such as nu0, nu0 plus nu-m, nu0 minus nu-m, 2 nu0, 2 nu0 plus nu-m, 2 nu0 minus nu-m, and so on. Nu-m corresponds to Raman active vibrations of the molecules. Then the hyper-Raman effect occur when molecule is exposed to an intense laser radiations. The result in scattered frequency is linear Raman scattering nu0, nu0 plus or minus nu-m, 2 nu0, 2 nu0 plus or minus nu-m. In hyper-Raman scatterings, the scattered radiations are at a frequency 3 nu0, 3 nu0 plus or minus nu-ms. The 3-photon process, that is the 2 incident photons interact, 1 scattered photon is emitted. The types of scattering, Rayleigh scattering, Stokes, anti-Stokes, hyper-Rayleigh, hyper-Raman Stokes and anti-Stokes. In general, the hyper-Raman scattering selection rule have the following characteristics. All infrared active bands are hyper-Raman active. All Raman active bands are not hyper-Raman active. Vibration which are both infrared and Raman active inactive are hyper-Raman active. Hyper-Raman active vibration which are IR active are always polarized. Then this is the schematic representation of hyper-Rayleigh and hyper-Raman scatterings. That is, in hyper-Rayleigh scattering 2 nu0 is the frequency and hyper-Raman Stokes 2 nu0 plus or minus nu-ms, Stokes and anti-Stokes. Then let's discuss the classical treatment of hyper-Raman effects. The electric field E associated with the incident radiation can return as E equal to E0 cos 2 pi nu t. Then the normal coordinates are Q equal to Q0 cos 2 pi nu n of t. N of t. Then expanding the chi1 and chi2 as a Taylor series in normal coordinates, we get the corresponding equations. Neglecting the higher order terms, substituting chi1 and chi2 in the above equations, we get this equation. Then this polarizability contains 8 distinct frequency components. They are at nu equal to 0, the DC field term. Then nu equal to nu0, the Rayleigh scattering. Nu is equal to nu0 minus nu-m, Raman Stokes. Nu equal to nu0 plus nu-m, Raman anti-Stokes. Nu equal to nu-m, molecular frequency. Nu equal to 2 nu0 hyper-Rayleigh and 2 nu0 minus nu-m, hyper-Raman Stokes. Nu is equal to 2 nu0 plus nu-m, hyper-Raman anti-Stokes are get. Then the experimental techniques for hyper-Raman effects. We have already said that the giant pulse lasers only can observe the non-linear susceptibility chi2. Then there are two methods for observing the scattered radiation of such low intensity. That is single channel detections and multi-channel detections. In single channel detection uses a grating dispersion system as a monochromator. The signal is weak, thus averaging over many laser shot is needed. Example 100 laser pulses per spectral elements. The time consumed is only 50 hours or 50,000 laser shot for 1000 spectral elements. Then the second one is the multi-channel detections. In multi-channel detection, capture all the spectral elements at one using, that is grating spectrograph, images and intensifier, multi-channel memory, faster digital data storage and less laser wear and tear, allow average across multiple laser shot to improve the signal to noise. Then this is the block diagram of the multi-channel Raman spectrometer, laser, sample, and the grating spectrograph, image intensifier, and multi-channel memory. The advantages of multi-channel detections are time efficient, less laser wear, real-time digital data processing, better signal to noise ratio. Thank you.